Bismillah. So in this video I will demonstrate how the results from the uh, mesh how the mesh results can be visualized in the preview Paraview, and also I will talk about the Navier Stokes equations for the step 57 in the DL2 example. So I am Asaf Istiak. This is a course of advanced numerical analysis which is supervised by Professor Sijo Kim. So here I will give a brief tutorial visualization and 2D and 3D files, uh, and also explain the 57 step 57. For 2D analyzation visualization, this is one of the 2D BTK file. I will use the Paraview here, right Paraview, and it will be opened automatically. If I click it here, then I will go to the 2D and just apply it. So if I click the right, hold over the right click, then it will be zoom and it will be rotated if we click it, and by left click we can transfer this one. So how about these are three which can be used for uh, further good visualization. This is for the surface with the edges. So here you can see the number of surfaces here, and also the solid color if you want that, and cell normals, and yeah, we need the solution. And this is the legend of the contour, so we can remove that from here, and we can adjust the color too with that one. Also there are other features. Let's say for example this is the contour. If we click it here, then the contour will be yeah, we can get the contour here, or there is a I button, so if I click it, then this function will be removed. And also we can see the value range here, 1.5 also, and there are other features also, coloring, styling, and yeah, also there are some informations which is very important. We can see the number of cells and number of points and polygonal mesh which is applied here. And yeah, what's more, we can go here and adjust the camera and select control, and there are other features for toggle selection, select cells, something like that. So we can also play it if the yeah if the file is quite big, so it will be run for a certain time. And this is the contour, you can see that, and we can also adjust the contour. Well, I'll just watch it, and I want to add a filter in an alphabetical way, and we can get the rough scalar. If I click it here, then there's some problem in my Paraview that I cannot hover over the 2D. However, this is the scalar 2D form, so if I get the mesh here, this will be something like that. And yep, now for deleting this type of elements, we just right click it and delete it, and I will delete, and I will import one of the 3D files. So if we just import a 3D file, maybe btk, then just apply it, and yeah, we can get the 3D object here. And then I will just for the edges, you can get the edges. And how about the contour? If we just click the contour here, then yeah, this is the contour. And also we can change the properties of the contours too, the maximum number of levels, like if I give it just 10 and apply it. And also just do it here. And how about the information? Here the information of the x, y to the z range. And if we go here, then we can slice it. Slice means here we can get one of the part of the 3D object. Also for slicing it, for slice we can get one cross-sectional area. Also if I want to just click it here, and if I want the meshes here of that portions, and we can get the meshes too, and get to the final one. Sorry, this is the slice. This is the basically slice, so we can get the meshes of the inner part, any inner part of the meshes, so we can get the slice like that. And other functions are maybe I can go to the filter alphabetical way. I'm not going to do this. It's actually not necessary for this is for elevation, and this will set the contour for the elevation here. And let's delete it. Okay. And more functions are, this is the threshold. So if I want the threshold here, then I just can get the high ratios area. Here. So if I increase this one and apply it, then we can get this type of visual condition. This is the visualization of a simple 3D component. Let's import another one which has more variables. So what happens if we run the Paraview for the many refined steps actually? So this is the step 22. If I run the Paraview here, then I will just, there are a lot of files here, so without selecting one by one, I will just select this one and press OK. So this is one of the velocity contour. So there are pressure contour and velocity contour. I will select the velocity. These are the magnitude to the x, y, z, whatever I want. Edges for this object, and also we can change the color from here too. And if I take the calculator here, I can calculate something like that. So and what about the contour? If I hit it, the contour looks like that, and there's some trade lines or streamline actually. So this is quite like this one. And what about the glyph? If I apply this one, then it looks quite interesting. So we can get the uh, glyph scale from here, or the vorticity, or the rotations, or something like that. Okay. Also, we can go to the rescale here, and you can run it under the time interval, and also adjust the color like the previous ones. Okay, another kind of example could be depicted here. Step 26. If you open Paraview and import its files, there are a lot of files. So if I select this one, the refined steps will be selected together, and I will apply it. So yeah, so there is a legend scale, but this is totally blue here. If I click the animation, then it will seem like this. So this is not actually like that. So what should I do now? We should just rescale it, then yeah, we can get a real visualization real visualization like that. Okay, also we can modify like the previous ones. So okay, first of all I will talk about the Navier Stokes equation in step 57. Well, in the documentation we can get the explanation here, but I will briefly explain it. In the Navier Stokes equation, um, here in this case actually the flow that they consider here is assumed to be steady, and in a domain of omega, which is depends on the Reynolds number, and the diameter of the Reynolds number is 2 to 3, and piecewise the piecewise smooth boundary. And here you can see the F, which is defined as a force field, and here U, which is the velocity field, and the P is the pressure field. Okay. Well, unlike the Stokes equation, there are also demonstration in Stokes equation in step 22, but this in that term the convective part was the u dot del u. So So the first step of computing numerical solution is linearize the system, and this will be done using the Newton's method. A time-dependent problem is also discussed in maybe step 35, where the system was linearized using solution from the last time step, and no nonlinear solve is necessary. So what about the cases for linearization? So they define a nonlinear function whose root is solution of Navier Stokes equation by this equation. So assuming the initial guess is good for to guarantee the convergence of Newton's iteration, denoting x of this x actually, yeah, this x will be dependent on the velocity and the pressure. So in that case, the Newton's iteration on a vector function can be defined like that. And if here x to the power k plus 1 is the approximate solution, where k is where the k is the step here, and I'm sorry, k plus 1, actually k plus 1 is a step here, and this x to the power k represents the solution from the previous step, and this part is the Jacobian matrix evaluated at the x to the power k, and a similar iteration can also be found maybe yeah, uh, we can find in step 15. Okay, so the Newton iteration formula implies that new solution is obtained by adding an update term to the old solution. So instead of evaluating the Jacobian matrix uh, and taking it in inverse, which is very complicated, so we can consider the update term as whole as update term like the others. So the final linearization system will be like this one. So here the UK and the PK are the solution from the previous iteration. Additionally, the right hand side here, this right hand side of the second equation, no, I'm sorry, yeah, this right hand side of the second equation is not zero, since the discrete solution is not exactly divergence free, and the right hand side here acts as a correction which leads the discrete solution of the velocity to the divergence free along Newton's iteration. So in the linear system, the only unknown of the part is this one and this one. These are the unknown part. Then we can use a similar strategy like the step 22, and now the Newton's iteration can be used to solve the initialization, maybe for initial guess for u naught for this one, and p naught, and the tolerance also, and linear solve to compute the update term, to update this term uk and del pk. Okay, and also we can update the approximation like that, this one, so we can get instead of this we can get the velocity or the pressure, or yeah, between these two, and also we can check the residual norm. Well, for the initial case, yeah, the initial case needs to be close enough to the solution of the Newton's method to convergence. Hence, finding a good starting of the value is very crucial. So here B, yeah, here B in the velocity is very large. A good initial guess can be obtained by solving the Stokes equation with the velocity. So with the problem dependent, so this works. The B is greater greater or equal than 1 by 400 for the solution considered here. So however, the convection term here will be dominant in the velocity if this convecting term actually will be dominant when the velocity is small, because if the velocity is small, then convection will be increased, and in that case what about the velocity? So the velocity would be it would be like it tends to 1 by so I'm sorry. So there would be some criteria of laminar and turbulent flow, and if we get the laminar flow, then we can get the convective term too. So in that case too, in this situation we use the continuation method to set up a series of auxiliary Navier Stokes with viscosity approaching to one of the target of Navier Stokes. So yeah, though the initial gauges are something different, but yeah, and the final gauge would be like that. In this process, the repeated sequence of viscosities Vi uh, and that determined experimentally, so that the final solution can used as a starting gauge of Newton iteration. So what about the preconditioner and the solver? So at each step of the Newton's iteration, the problem results in solving saddle. There would be some saddle point like that. So this is the sparse matrix, and like the previous equation, uh, based on the previous equation, this is quite like the same. And okay, so last of all, the test case here. So we use the lead driven cavity flow as for the case in the previous ones. Um, the computational domain in the actually, yeah, there are some examples of this type of cavity flow in the previous steps. The computational domain is the unit square, and the right hand side is f is equal to 0. So from that condition, obviously, if y is equal to 1, then we will get this condition, and otherwise we will get that condition. So in the code we will apply the if or else, and so when we will solve this problem, the error consists of nonlinear error, and the nonlinear parts decreases with each Newtonian iteration, and discretization error reduces the mesh refinement. So in this example, actually the solution from the coarse mesh is transferred to successively finer meshes and used as the initial gauge. Therefore the nonlinear error is always brought below the tolerance of Newton's iteration, and the discretization error is reduced with each mesh refinement. So here the cavity refinement of Reynolds number, they have considered um, two types of Reynolds number. First of all is 400, and second of all is 7,500. So for these two Reynolds number, um, the viscosity actually defined on the Reynolds number, obviously. Uh, if the Reynolds number is 400, then viscosity will be 1 by 400, even though we can still find a solution for Reynolds number 10,002, and the references contain the results of comparison, so we can limit the discussion here just for the 700 and 7,500. This is because the solution is no longer stationary, starting around 8,000, but instead of becomes periodic for details. So now I will show the code here in their documentation. This is the code for 57. I will briefly discuss the code base here. So instead of, yeah, they have used the namespace of for the 57 and use the template of and the template's name is team, which is a class template, and there are the member variable and the member function. Okay, so the member variable are 1 2 3 4 5 6 7 8 9 10 11 12 13 14, yeah, like 14, and we can get the members too. This class actually manages the matrices and vectors described in the introduction, and in particular the block vector for the current solution, current Newton update, and line search update. So for the boundary values in the right side, in this problem the velocity along the upper surface of the cavity to be 1 and 0. Yeah, 1 and 0, and also this value will be on the other three walls too. So the right hand side function is 0, so we do not need to set the right side function in here. So the number of the components of the boundary functions is here. So the number of the if I set the dimension 2, then the number of the components will be 3 and something like that. So the ultimate use of vector tools here. So later the ultimate use of vector tools interpolation boundary values to set the boundary values, which requires the boundary value functions to have the same number of components as the solution, even if they are not used. Okay. So how about the preconditioner? Yeah. This portion is for the preconditioner, where the viscosity, sparse matrix, pressure, and the inverse sparse matrix are described here. So as per the theory, the preconditioner is an iterative method which is implemented as a matrix vector operator actually. So in practice, The preconditioner is decomposed as a product of three matrices. So here the three matrices can be the inverse matrix, A inverse, the first vector involved with a solve of the linear system, and here the system via the direct solver for simplicity also. And this first matrix is the star component on the theory the preconditioner is dependent on, and we will go through the class preconditioner here. So we can notice the initializer of the inverse of the matrix at the top left corner, and is completed in the constructor. So matrix vector will be like this. So how about the stationary class implementation? Yeah, here. So here, like the step 22, the Lagrangian coefficient gamma is uh, declared here, and also we can get the degree of freedoms, and how we can detect the degree of freedoms with the DOF handler. Actually, it enumerates the degree of freedoms and constrains the current mesh. Okay, so if I go in details, then for the yeah for the DOF handler of distributor of this line, actually the first step of associate of degree of freedom are given a mesh. Then this output uh, we renumber the components to have the velocity of degree of freedom. Yeah, here that actually comes before the pressure degree of freedom to able to split the solution vector in two blocks. And then the Newton schemes that will be applied for the boundary condition to make sure the boundary condition remain satisfied during Newton's iteration. Okay. Similar to step 22, the conditions are yeah stated here for getting the refined meshes. So we can get the local matrix, yeah, Reynolds number, degree of freedoms, and the matrix, and also the system Reynolds number. Also, if it these conditions didn't satisfied, then it will print this one. Okay, let's get to the solver equation. Here the solver equation they use as solver control, yeah, that's a solver matrix. So if we have other types of the tools for visualization such as the NVIDIA, then we can also get the we can also follow the parallel solver too. So in solving the parallel solver, it needs the very strong system. So yep. In this condition, this solver is used. And how about the Navier Stokes? Yeah, the refined mesh. The refined mesh is the conditions for the refined mesh are described in this section, and also For the Newtonian iteration, the conditions are set here. So what are the conditions? The conditions they set here: the degree of freedom, and they initialize the system and present solution. And in the first system, they have this called the assemble system too. So in the first step, if this doesn't if this is not true, then it will print the this portion. And what is about the Newtonian's iteration? So if we want to get the Newtonian's get the knowledge about Newtonian iteration, we can get to the documentation, and this is actually the arguments for that. First argument will be defined here, and if it doesn't applies, then we will get to the else value. However, let's get to the run option. Well, in the run option, we have they have considered the Reynolds number 1000. So with that 1000, this will be run, and the Newton iteration will be will check whether it's true or not. And also we can change the refine mesh number. So here the mesh number is 5. So if we just click here and press 2, then it will be 60. And if we press here the 4, then it will get 256. Now we will get 124. Yeah, 124 meshes maybe. And also the viscosity is dependent on the Reynolds number here. So for stationary Navier Stokes, if we define the dim is equal to 2, and then we can get the results from the int main portion. So how about the result here? They have demonstrated the results here. Actually, the results for the low Reynolds number, the residual, this is the table, and they have mentioned the velocity and magnitude here. So the solution is compared with the this solution, and also the horizontal velocity versus the y coordinate. And for the high Reynolds number, the loss convergence is like that for total iteration. Here the horizontal velocity is quite different. In the initially this dropped, but in the laminar or in the lower Reynolds number, it was developed consequently. And this is the velocity magnitude, which is more dense here. Like that. So I've already run the I've already run the step here. So these are the BTK files. So how to visualize it? We'll use the Paraview. There are a lot of BTK file that has been created for the refined mesh. So if I click it here, total, and apply it, it doesn't look good, so I will use the visit. For 57, so we can go to that folder. I have already make it and run it. So here is the command. First I have cmake it, then after cmaking it I have make it, so it was 100% with run made, and then I have right dot slash step 57, and this has completely run, and these are the, you can see there are adaptive meshes here, and you can see the steps and the number of the lines on the each, and here after running you can get, I have used visit for visualization, and you can get the files. Here are almost a lot of BTK files. So how we can see it, we can visualize it by visit. Here we are going to visualize by visit, and I have to select it, and all the BTK file will be selected, and I will go to the shadow color to make a color and draw it, and this is the basically 2D. And if I wanna add some meshes here, then and also the contour, this is the contour for the velocity magnitude, and also for mesh we can draw that, and for velocity magnitude, these are the velocity magnitude contour. And I don't need this type of annotation, so I will close the annotation here. Okay, let's keep it. Then what can we do more for good visualization? So I will elevate that, always apply yes and dismiss, and I will draw it. So here you can see the elevated velocity magnitude, the velocity contour here. So if I play it, how it will look like. So there's some bugs, maybe some plots had errors, so visit will regenerate these plots. Okay, so these are pretty nice to see it, and we can delete the annotation, like no annotation. There's some problem in my screen, so I will fully extend the screen and apply and dismiss. So here are the velocity contour of the Navier Stokes equations, the finite unit analysis. Okay, thank you.